it is understood that the top of the coil behaves like the North Pole and this one behaves like the South Pole. So because of this behavior of two ends, north and south, and the bottom end of the coil is bottom end of the bar magnet is the north, we feel a repulsive force. So against the repulsive force, that is why when you push the magnet, the magnetic flux now covers more number of turns. So the magnetic flux is increased, and due to that, the coil and the galvanometer behaves as a closed circuit. So in the closed circuit, due to the change in magnetic flux, by pushing the magnet towards the downward direction, the induced current flows. That induced current will be flowing in the opposite direction of the motion of the bar magnet. So now we are proving that the motion of the bar magnet is opposed by the induced EMF induced in the closed circuit. That is why we feel repulsive force. We could not be able to move the magnet towards the downward direction so freely. Suppose if you decide to pull the magnet away from the coil, what happens? You feel an attractive force. So this behaves, that time this becomes south pole, this becomes a north pole. So direction of the induced current flowing in this closed circuit will be in opposite direction. Again, that will oppose the motion of the magnet if it is pulled in the outward direction. So this shows that the direction of the induced current produced in the closed circuit of the coil and galvanometer opposes the motion of the bar magnet. This is based on the Lenz's law. So against the repulsive force or an attractive force, if you move the magnet in the upward and downward directions, you are doing a real mechanical work. That mechanical work is actually converted into electrical energy in the name of induced current. Whenever current flows in the circuit, as per the Joule's heating law, what will be produced? Heat is produced. So the mechanical work that you do with the bar magnet is so converted into electrical energy and heat energy. So now the Lenz's law is actually involving in this particular concept. That Lenz's law is involving based on the conservation of conversion of one energy into another energy. So we can prove that the Lenz's law is based on conservation of energy. Now the Fleming's right hand rule. So as you have studied the Fleming's left hand rule, you have to point in 3 fingers of your right hand and kept mutually perpendicular to each other, and then 4 fingers indicates the direction of the magnetic field, and then automatically the thumb shows the direction of the force experienced by the wire carrying current, and automatically this middle finger indicates the direction of the flow of a current in the conductor. Then the self-inductance. The next topic is called self-inductance. So the property of a coil which is producing electromagnetic induction on its own when the change of current flows through the coil is called self-induction. For example, you consider a coil just connected to a battery and key. When key is closed, the current is delivered from the battery from this direction. When current delivered by the battery, the growth of the current delivered by the battery gradually increases. This is how normally happens. So when the current gradually increases, the flux associated with the coil gradually increases. Suppose if the current goes in clockwise direction, the magnetic field will be from left towards the right. Due to the gradual growth of the current, the number of magnetic lines of force will gradually increase from 1, 2, 2, 3 and so on and so forth. So as per the phenomenon of electromagnetic induction, whenever there is a change in magnetic flux linked to the closed circuit, what is produced? The electromagnetic induction is produced. So due to the gradual increase of current, the number of increase of lines is the change in magnetic flux linking the same coil. So within the same coil, another current, the EMF is induced in the opposite direction. So due to the induced EMF, induced current is flowing against the inducing current. This I is the inducing current, I is the battery current, and serves as the inducing current. And due to the inducing current, due to the change in magnetic field, another opposing EMF is produced. And due to the opposing EMF, and induced current is flowing against the inducing current. Induced current flows against the inducing current. And next one, a coefficient of a self-inductance. So in this topic, you may get one more question. So with respect to the coil and the battery and key, as I have drawn earlier, you can say that the flux produced in the coil due to the change in the current flowing through the coil. So the flux of a coil is directly proportional to what? The current flowing through the coil. If you want to equate it, phi is equal to what? Li. L is the constant of proportionality. This L is otherwise called coefficient of a self-induction or self-inductance. There are two names. L refers what? L refers what? Coefficient of a self-inductance or coefficient self-induction of a coil or self-inductance. So if I say, if I pass 1 ampere current through the coil, then I can say L is equal to phi. Then I can define what is called self-inductance of a coil. The coefficient of a self-inductance of a coil, just listen to the equation, you can easily learn 1 3-mark question. The coefficient of a self-inductance of a coil is numerically equal to the magnetic flux linked to the coil when unit current flows through it. It's a 1 3-mark question. The next one, we know that according to the second law of Faraday's laws of electromagnetic induction, E is equal to minus d phi by dt. And where phi is equal to Li, so you can say E is equal to minus d by and dt of Li. So L is a constant, you can take it out. So E is equal to minus L into di by and dt. So now from which you can able to understand, when I by dt, rate of change of current in a coil is 1 ampere per second, is equal to 1 ampere per second, we can say L is equal to minus E, correct? I hope you can able to follow me. So from this I can say the coefficient of a self-inductance of a coil is numerically equal to opposing EMF when 1 ampere current flows in 1 second in a coil. So based on the equation you can easily define. There are two definitions for the coefficients of self-inductance. The first one is so easier and second one is a bit tougher. So better you write the first question if it is asked in the examination point of view. So from this equation I can modify that L is equal to minus E by di by dt. When rate of change of flow of current in coil is 1 ampere per second, and suppose if the EMF is produced is equal to 1 volt, then L is equal to what? 1. But what is the unit of coefficient of inductance? Inductance has got Henry, so 1 more question. So you will get 1 Henry. Now we can define 1 Henry. 1 Henry. So 1 Henry is a coefficient. 1 Henry is a coefficient of a self-inductance of a coil, self-induction of a coil, in which when 1 ampere current flows in 1 second, produces the opposing EMF of 1 volt. So these are the important definitions that you should understand from the topic of a coefficient of a self-inductance. Now we are going to derive the self-inductance of a long solenoid. Self-inductance of a long solenoid. So I am going to draw a long solenoid having some n number of turns and having some definite length and area of cross section A. So this is the length. I can say this is the length of a solenoid and having area of cross section J and also having some n number of turns. If I want to calculate, you know that in third chapter I have derived the expression for the magnetic field produced by a long solenoid. So B is equal to mu naught Ni. The same formula, the N is the number of turns per unit length. The same formula can be modified as N by L, where N is the number of turns per unit length. So B is equal to mu naught Ni by Nl. So if you want to calculate magnetic flux in 1 turn, so flux general formula, basic formula for flux is phi is equal to Ba cos theta, and theta is the angle between the area of the normal drawn to the area of the coil magnetic field. Automatically for the solenoid, the theta, that is angle between normal drawn to the area of the coil and the magnetic field is 0, and cos 0 becomes 1, becomes a Ba. The flux per turn of a coil, flux per turn of a solenoid, I can say flux per turn is equal to magnetic field produced by per turn, I can say per turn into the area of the coil. What is the magnetic field produced by per turn? This is equal to, I can write this as a P turn. So I can write flux per turn is equal to mu naught N I by L into A. Mu naught N I by L into A. So if you want to calculate total flux, the total flux is equal to flux per turn into the total number of turns of a solenoid. So it is equal to, phi is equal to mu naught Ni A by L into N. N comes twicely, so we have to multiply. So phi is equal to mu naught N squared A by I by L. Since we are talking about only a one solenoid based on the self-induction, so I can write phi is equal to Li. So the I can be removed. So L is equal to mu naught N squared A by L. So this is a formula for calculating the self-inductance of a long solenoid. So next we will move on to the energy associated with an inductor.